And the first flash talk is by Jiménez Lopez. And it is about charge injection, carrier recombination, and HOMO energy level relationship in Perovskite solar cells. Okay, there we go.
Charge injection, carrier recombination, HOMO energy level relationship in perovskite solar cells that we published last year in scientific reports. So in case you want to access to the publication, here it is the citation. Okay, our focus on this research was try to implement several semiconductor polymers widely used in organic solar cells such as PTV7, P3HT, and PCPDTVT, and compare them with the standard molecule as it is the spiral on top. So our main characterization was first JV curves, then we moved into time-resolved photoluminescence, and we use our transient techniques such as transient photovoltaics, and in my case, as my colleague Hilario told you, I use transient photocurrent and differential charging. Okay, so from the analysis of our JV curves, we obtained very good results, but either way, we observed very big differences in both voltages and JSCs. So we are going to try to explain why are these big differences. Also because on the voltage, we don't see this relationship on the HOMO levels, as it was expected. So our first approach to the study of recombination was by measuring the VOC and JSC dependence with the light intensity. From the VOC analysis, we can obtain if we have, we obtain from our fitting our ideality factor, and if it's 1, it will tell us that it's a direct free carrier recombination, and with ideality factor bigger than 1, the recombination will be by trap mediated. Also with the JSC analysis, if we fit it to a power law dependence and our alpha factor is close to 1, the charge carrier recombination at JSC will be negligible. From the analysis of the voltage dependence, we obtain that the trap-mediated recombination is the predominant in these devices. And from the current analysis, we obtain that the free carrier recombination as short circuit are negligible. That condition will be important also for applying the differential charging. Okay, then we move into the time-resolved photoluminescence. So we did it with films containing glass, the perovskite, and the whole transporting material. By the way, I forget it. Perovskite I used was the methylammonium lead iodide perovskite, and we measured the photoluminescence at 760. That is the emission of the perovskite. So we use it to study how efficient it is, the whole transfer from the perovskite to the whole transporting material. So the better the whole transfer, the less intense will be the photoluminescence, and the longer will be. In this case, we obtained that the better whole transfer was found for spiral ONTAT, then for PTV7, P3ST, and PCPDTVT, which correlates with the different currents that we obtain from the JV curves. After that, we move into our transient techniques. First of all, we measure our transient photovoltage, obtaining for all the devices a monoexponential fit. So what does it mean, our monoexponential? That we are only studying one kind of processes on this time scale. So we are correlated with a good coverage of the perovskite, so a good quality of the film as it can be seen in the SEM images. This is supported by our previous publication or ACS energy letters. So when we fit it on applying different at different light intensities, so different light biases, we can fit it all the decays to an exponential and obtaining a constant decay that is called beta. This beta constant is the constant decay, and it also correlates with the different currents. So first, the bigger will be for ONTAT, PTV7, P3ST, and PCPDTVT. Okay, so why am I using differential charging. In this case, with methylammonium lead iodide perovskite, our charge extraction is slower than the TPV. So that means that the recombination will be faster than the charge extraction. That couldn't be. So we use differential charging, that is an indirect estimation of charges, and it's a combination of TPV and transient photocurrent. From the TPV, we took the delta V at different light intensities, and from the TPC, as it is the charges generated by the laser pulse, this will be the same under every different light intensity. From that, we obtain the differential capacitance. It is fitted here, and it's interesting also in the differential capacitance to observe the shift in the different voltage, the higher voltage that correlates also with the VOCs of our devices. Integrating these curves, the area under these curves, we obtain the charges stored in the solar cell. Also, we can feed it to an exponential feed, obtaining this gamma factor that we are going to use now to estimate the recombination current. Why are we going to use the recombination current? It's when we are measuring at one sun, all the charges generated should recombine. So the recombination current should be the same as the JSC. To estimate the recombination current, we take the charges stored at the solar cell from differential charging at one sun, and we divide it by the order factor, taking the beta from the exponential fit of the TPV and the gamma from the exponential fit of the differential charging. And finally, it is multiplied by the lifetime at one sun taken from the TPV. With these results, we obtain very accurate recombination currents compared with our JSCs. So we can say that the TPV is a method that describes the recombination at the interface between perovskite and whole transporting material, and that the differential charging is a reliable method to estimate the charge stored in the device. So our conclusions are future work. So we fabricated efficient perovskite solar cells with different whole transporting materials. I compared their performance with the spiral ONTAD. The differences in VOC led us to suggest that VOC is limited by trap-mediated charge recombination, and also the measurement of the perovskite luminescence in the presence of the whole transporting materials shows that the most efficient whole transfer is for spiral ONTAD. And also with the differential charging and the transient photovoltaics, we obtain the recombination current, which is in good agreement with our JSCs. And also some work has been done with femtosecond transient absorption spectroscopy, but this is still a work in progress. Okay. And finally, thanks to my research group and all of you for your attention. And if you want to check my poster, it will be on poster place number 21. Thanks.